There is a single question at the bottom of physics, of chemistry, and of every scientific discipline in between. It takes into consideration every possible natural phenomenon of the universe, from the physics of water droplets to the chemistry behind color, from the behavior of atoms to the formation of black holes. In the 80 years since it first came up, no one has found a definitive answer to this question because there may not be a definitive answer to this question or any answer at all. But nonetheless, in this video, we will be trying to find one. We will explore where this question even came from, what the possible answers are, if there are any, and what those answers reveal about the nature of humanity. But in order to understand the nature of such a task, we have to ask ourselves one simple question. What is a second? Okay, hear me out. I know it sounds stupid, and it sounds like a really dumb question with a really obvious answer, but if there's anything that science has taught me, it's that there is almost no such thing as a stupid question. So let's take a second and just think about it. Here I have with me a piece of cesium-133, or at least something that looks like it because I can't actually afford it. Today, if you Google the length of a second, you'll stumble across this answer. 1 second is the time that elapses during about this many cycles of radiation produced by the transition between two levels of the cesium-133 atom. Cesium is actually the element used to make one of these boys, atomic clocks, and for good reason. If you were to start one of these 150 million years in the past, back to when the Stegosaurus existed, and started running one of these clocks, that clock today would be off by 1 second. This thing, that's how accurate this little thing is. Like, what the heck, man? But the problem with this definition of a second is that we've been using the second in calculations and measurements for a lot longer than we even knew cesium existed. So what was the original definition? The origins of the second trace back to the 1000 AD by the Persian scholar al-Biruni. But he defined the second based on the fact that the day, the time it takes for the sun to pass the same point in the sky twice, is 24 hours long. Well, why 24? That's because the ancient Egyptians divided the day into two 12-hour parts. Well, why 12? And eventually, after wondering how you even got this far, you find what you think is the end of the rabbit hole. At around 3500 BC, the ancient Sumerians, who at the time lived in modern-day Iraq, devised the sexagesimal math system that was based around the number 60 and 360, which probably came from the year, which is how long it takes for the sun to climb up and climb back down the sky back to the same place. Okay, that was a lot of info. Let's just climb out of the rabbit hole for a second. 1 second got its definition and meaning from how long 1 year is. But hear me out. What if the Earth were a little closer to the sun? What if the sun were a little smaller? Would we still use the base 60 system? And in turn, would a second still be a second long? So isn't there a little bit of chance to it all? A bit of randomness? I mean, I don't know. Maybe. Okay, look, we all know the story of Isaac Newton. In 1660, an apple fell on his head, and with a few strokes of human genius, he was able to derive his 3 laws of motion. However, there is a 4th theory that doesn't get as much attention, but is still crucial to the way that we understand the universe. His universal law of gravitation. Imagine you're on a flat field, and you try to jump up. The reason why you don't fly away into the stratosphere is because of Earth's gravity pulling you back down. What Newton realized was that gravity is also the force that keeps the sun in orbit around the sun. But how could two completely different types of motion, one in which you almost move in a straight line, while another in which the Earth moves in almost a circle, both be caused by gravity? So Newton devised an equation and theory to explain this. It basically says that as either of the two objects get heavier, then the gravitational pull between them must get stronger by the same proportion. And if the two objects are farther away from each other, then the gravity gets weaker by an even greater proportion. But there was a problem with this theory, and Newton knew this. If Newton had two hypothetical planets that were a meter apart from each other, and each weighed 1 kilogram, then the gravitational force between them would not be 1 Newton. It would be way less than that. Otherwise, the gravitational force between you and the chair would be so strong that you physically would not be able to get out of it. So, on the right side of the equation, there has to be a number, a universal constant, that makes this equation true. But by this point, Newton was focusing on other things, and he died in 1727 with that mystery unsolved. 51 years later, however, it was finally discovered. And the most interesting part about it is that it was almost completely by accident. '18th century English physicist Henry Cavendish was an interesting man, to say the least. He didn't really care about the world around him except through his scientific lens, and he barely published any of his work. And the work that he did publish is unique, to say the least. In 1776, he published 3 separate papers on factitious airs, including flammable air, which we now know as hydrogen. He was also one of the many scientists trying to find the elusive phlogiston, hypothetical element that was supposedly responsible for all combustion reactions, like the explosion that happens when you burn something like methane gas. Clearly, science has changed a lot since then. But I can't lie, Cavendish was pretty smart because of how he was able to calculate the mass of the Earth and, in turn, find G. Let me show you how he pulled this off. Imagine that you have a large box. Hanging from the ceiling of the box is a wire connected to a tight horizontal string with 2 heavy lead balls on each end. From a lower horizontal string hang 2 smaller lead balls fixed in place. Of course, there were various machines that Cavendish used to control the position of the large balls and look at the equipment from the outside of the box. Now, the reason why Cavendish needed this box is the same reason why you can actually stand up from your chair right now. The large lead balls, because of their gravitational pull on each other, would be very weakly attracted to the other. And I mean the force is as small as 1 in 50 millionth of the force that the Earth would exert on the balls. Wait, can we stop for a second just to appreciate that? Cavendish was able to create an experiment in the 1700s that could detect a force equivalent to that of an earthworm pushing against a wall. Any slight gust of wind or maybe even a breath near the apparatus could completely mess up calculations. I mean, that's dedication right there. Anyways, the large lead balls would ever so slightly, because of their gravitational pull towards each other, speed up until they collided with the small lead balls. By measuring various aspects of the experiment, like the distance covered by the large balls, combined with some clever math, Cavendish was able to calculate the mass of the Earth. But wait a second. Look at the equation for the law of gravitation. We have the masses of 2 objects attracted towards each other, the radius of the distance between the objects, and the gravitational force between the objects. Without even realizing it, Cavendish gave us all we needed to calculate the value of G. If you'd like a more detailed explanation of this experiment, I highly recommend checking out this video right here. And there it is, that's the gravitational constant, one of the fundamental constants that controls everything that could possibly happen in the universe, period, from the motion of falling objects to the orbit of planets. For the next 150 years, this single number served as the foundation for modern physics and astrophysics. And to this day, Newton's classical theory still gives very accurate descriptions of how gravity works. But there is still something deeply mysterious about this number, and it puts into question the existence of the universe. And in 1961, that question was shoved into the limelight.